First, let's imagine that I walk 10 meters in the x direction. In other words, along the x-axis. And then I'm going to walk 5 meters in the y direction. So my question is, what is my net or total or overall displacement vector to describe the combination of these two individual displacements? Well, let's draw it out. Let's draw our coordinate system. And I'll use our standard coordinates of x and y. So here's x, here's y. Our first displacement that I will call d1. So this is our first displacement vector, d1. Now it doesn't matter where we start. We can start at any arbitrary point. We can start there if we want. I'm going to walk 10 meters in the x direction. So my first displacement will look like that. I'm walking in the x direction for a distance of 10 meters. That's d1. Now what do? We take our second part of our walk, which will be 5 meters in the y direction. Well, where do we start that? Where did we start this part of our walk? Well, we started over here. We've already walked from here to here. So we start the next part of our walk from this point, where we ended up after the first part. So the next part, or the next displacement, will start here and go in the y direction for 5 meters. And that's going to be our second displacement. We'll call that d2. So this is d2. So my question is, what vector could we use to describe our overall displacement? In other words, what vector goes from the initial point where we started to our final point where we ended up? Well, we started out at this point, and we ended up at that point. So the vector that describes the overall displacement would look like that. It goes from our initial point where we started to our final point over here. We'll call that our total displacement d. And what we're going to do is we're going to say that our final displacement, our net displacement or total displacement, is equal to the sum of our two displacements, d1 and d2. So we're going to say that d is equal to d1 plus d2. D vector is equal to d1 vector plus d2 vector. Now, what is d? D is a vector that goes from here to here. It has this magnitude from here to here, and this direction up this way. Now, how can we describe d? Well, we can give its magnitude and direction. We can say how long it is, and we can say what the direction is. Well, to describe its direction, if we could figure out, say, that angle there, we'll call that angle theta. If we could figure out what that angle was, theta, we'd be able to describe the direction. And the length, if we could figure out what the length of that vector is, that would be the magnitude or the size of the vector d. Now, be careful. You cannot just say d1 is 10 meters and d2 is 5 meters, so d must be 15 meters. No. That would be just adding the scalar magnitudes. We cannot add the scalar magnitudes. We have to add the vectors. How do we find the magnitude or the length of d? Well, we happen to know that these two vectors are perpendicular to each other. So we can actually use the Pythagorean Theorem to figure out what the magnitude of the hypotenuse of the triangle is. So we know that the magnitude of this vector, which we'll write as d without the vector sign, is going to be the square root of the sum of the square of the sides. So 10 meters squared plus 5 meters squared root. We evaluate that, and what we find is that d is equal to 11.2 meters, and I've kept it to 3 sig figs. So the magnitude of our resultant vector d is 11.2 meters. Now, how do we find the angle? Well, we remember trigonometry. We know that tan theta is equal to opposite over adjacent. In other words, 5 over 10. Or 0.5. So theta, if tan theta is equal to 0.5, theta is the inverse tan of 0.5. We take the inverse tan of 0.5 and we get 26.6 degrees. There we go, 26.6 degrees. For this course, for all of this course, and also all of 1112, if you take 1112, I will always be using degrees anytime I use a trigonometric function. We will be using radians later on in this course, but we'll never be taking trigonometric functions of angles in radians. So make sure your calculator is always in the degrees mode. If, when you take the inverse tan of 0.5, if you get 0.4636 or something, you're in radians mode. And make sure you change that and put it into degrees mode so that when you take the inverse tan of 0.5, you get 26.6. So make sure that, that you take care of that. So we can then finally describe our resultant vector by giving its magnitude and direction. D is equal to 11.2 meters at an angle of 26.6 degrees above the x-axis, or the x direction. We've got to make sure that not only do we give the angle, but we say, what's the direction relative to an axis? So this is above the x-axis. If we just said 26.6 degrees, we don't know. Does that mean 26.6 degrees below the x-axis, or 26.6 degrees from the y-axis, or what? It's not clear exactly what the orientation is. So we've got to make sure that we give that orientation to the particular axis. Okay, great. So this is how we can combine two vectors. And in this case, they happen to be perpendicular to each other. What if the vectors are not perpendicular to each other? Well, it's a little bit more difficult, but not a whole lot more difficult. So let's try another one. Okay. Let's imagine we are going to go for another walk, and we've got two parts to it. Let's say our first part, and this time I'm just going to call it a vector A. A is 124 meters at 15 degrees above the x direction. X-axis or x direction, it's the same thing. And our second part, B, is 50 meters at 25 degrees above the x direction. Okay, let's see if we can figure out what is our resultant vector, our resultant displacement after these two. Well, again, let's draw it. Just qualitatively, what's the motion going to look like? So let's draw in our x and y coordinates. Our first vector, A, is 124 meters, 15 degrees above the x-axis. So say 15 degrees above the x-axis, something like that. There's 15 degrees, and this is 124 meters. So there's A. Now, B, where does B start? Well, B starts where A ended up. So we're going to start drawing B at that point. We're going to go at an angle of 25 degrees, so that's going to be a little bit steeper than A, for only 50 meters, so it's going to be not quite as far, so something like that. So this is going to be 25 degrees. And this is 25 degrees above the horizontal, not above A, but above the horizontal, and 50 meters. Okay, so there is B. Now, what's our final resultant displacement? Well, again, this is where we started. This is where we ended up. So our resultant displacement is going to go from the initial point all the way to the final point, and we'll call that our resultant displacement C. So that C vector is equal to A vector plus B vector. Okay, there we go. Now, let's see if we can figure out how do we describe C? How do we do that? Well, we need to give its magnitude and direction. So how do we figure those out? Well, let's see. A and B are not perpendicular, so we cannot just use Pythagoras to figure that out. But we notice, well, C, we could still make a big triangle like this for C. And we notice that if we take A and break A down into its x and y parts like this, and we break B down into its x and y parts like that, well, the x parts could combine and the y parts can combine. So let's see, what am I really saying here? So here's the vector A. Here's A. Now, A is above the x-axis, but if we could break A down and figure out what this part is, the part of A that points along the x-axis, we'll call that A sub x. And this part here, the part of A that points upward along the y-axis, we'll call that A sub y. A sub x and A sub y are what we call the components of A. The x component of A and the y component of A. Now, B, here's B. B points along the x-axis this much. So that's what we'll call B sub x. That's the x component of B. And this is how much B points along the y-axis. Whoops. So that's the y component of B. Now, what do those have to do with C? Well, we notice here's C. This is the x component of C. And we notice that the x component of C is the x component of A plus the x component of B. So C sub x is nothing more than AX plus BX. And notice that this side is the part of C in the y direction. So this is C sub y, the y component of C. And we notice that C sub y is A sub y plus B sub y. So C sub y equals AY plus BY. So we can find the components of C, Cx and Cy, if we first find the components of A and the components of B, and then we combine the x components and we combine the y components. And that will give us the x and y components of C. But then how do we find the magnitude and direction of C if we have the components? Well, that's exactly what we did the first part, where D1 was like the x component of D, and D2 was the y component of D from the first example. So all we need to do is figure out, can we find AX and AY? Well, actually, that's pretty straightforward. If we think about A, here's A. A has a magnitude of 124 meters and is at an angle of 15 degrees. This is AX, and that's AY. Well, from trigonometry, again, we know that the cosine of 15 degrees is equal to the adjacent side over the hypotenuse. In other words, A sub x over 124 meters. So A sub x is 124 meters times the cosine of 15 degrees. While the sine of 15 degrees is equal to the opposite side. Opposite of 15 degrees is AY, so that will be AY over the hypotenuse of 124 meters. So AY is 124 meters sine of 15 degrees. So we can find the components of A, in other words, AX and AY, very easily using trigonometry. Well, it turns out that AX is then 124 cos 15, that is 120 meters. And AY, which is 124 sine 15, that is 32.1 meters. So we've got the x and y components of A. Now what about B? Well, B, I'll draw it up here. Here's B. B has a magnitude of 50 meters at an angle of 25 degrees, where this is Bx and that is By. Now, I'm going to skip a step typically. Rather than going from sine and cosine, I'm going to go right over to this part here. Let's just remember that the adjacent side is always going to be the hypotenuse times the cosine of the angle, while the opposite side is always the hypotenuse times the sine of the angle. So the adjacent side is Bx. So I'm just going to go right to Bx and say Bx is 50 meters cosine 25 degrees. While By, that's the opposite side, that is 50 meters sine 25 degrees. Well, when we multiply that out, we find that Bx is 45.3 meters and By is 21.1 meters. There we go. So we have both Ax and Ay and Bx and By. We're going to combine Ax and Bx to find Cx. We're going to combine Ay and By to find Cy. So I'm going to erase all of this part here and this part here. And let's remember those numbers that we found. We've got Ax is 120 meters and Bx was 45.3 meters, while Ay was 32.1 meters and By was 21.1 meters. And we get Cx is equal to 165 meters. Notice we can only keep it to the units place. We have to drop the tenths place here. So 165 meters, while Cy is equal to 53.2 meters. There we go. Now what do we have? Well, now we're back in the position where we were with the last example with D1 and D2, where Cx is 165 meters and Cy is 53.2 meters. And what we want to find is what is the magnitude C and the angle theta. And what we find is that C is equal to the square root of the components squared and added. So that's going to be 165 meters squared plus 53.2 meters squared root, which gives us 173 meters, while tan of theta is equal to opposite over adjacent. In other words, 53.2 meters over 165 meters. Dividing that out, take the inverse tan, and we find that theta is equal to 17.9 degrees. And there we go. We've got our final vector C, which is 173 meters at an angle of 17.9 degrees above the x-axis, or the x direction, either one. There we go. And there is our final resultant vector C. So let's keep in mind, how did we combine the two vectors, A and B, even when they aren't perpendicular to each other? Well, we find the components of A, Ax and Bx. We find the components of B, Bx and By. The x component of C will be Ax plus Bx. The y component of C will be Ay plus By. We find all of those, we combine them together, then we can find the net magnitude of C by combining the components Cx and Cy. We find the direction using the inverse tan, and we get the magnitude and direction. And there we go. There is the final resultant C. Okay? There's lots of practice of these on the homework. All right. Now, for this example, for both of these examples, we had vectors that were both pointing in the first quadrant. In other words, they were pointing to the right and upward. Both D1 and D2 and A and B were always to the right and upward, or to the right and upward. However, this whole process works no matter what the direction of the vector is. Just keep in mind, let's imagine you've got some general vector V. If it is pointing to the right and up, this is assuming that we use our standard coordinate system of x positive to the right, y positive up, which you don't have to, but let's just assume for the moment we are. In this case, if the vector is pointing to the right and up, then we'll have our x component is positive and our y component is positive. If we have a vector that is pointing to the left and up, pointing to the right means positive x component. Pointing to the left means negative x component. So in this case, the x component would be negative. But again, pointing upward will mean our y component is positive. Pointing down and to the left, well, pointing to the left means negative x component. So Vx is negative. But pointing down will mean negative y component. So in this case, Vy will also be negative. And then pointing down and to the right, so what's that? Pointing to the right means what kind of x component? Positive. So Vx would be positive. But pointing down means what kind of y component? Negative y component. So Vy would be negative. There we go. So you could have vectors pointing in any quadrant, and you would just end up with a positive or negative component. And then, to combine it with another vector, you just use the component as either positive or negative. And you can either add it to the other component, or you'll get a smaller number. So it doesn't matter. Just use whatever the component is, whether it's positive or negative. And then likewise, if you have a vector that is perfectly horizontal, what kind of x component would that be? Positive. What kind of y component would it be? 0. If it's not going up or down, it'll have a 0 y component. A vector that points to the left would have a negative x component, 0 y component. A vector that points straight up will have a, what kind of x component? A 0 x component. And what kind of y? A positive y. What kind of, okay. And then if it's pointing straight down, what kind of x? That would be a 0 x component. What kind of y component? A negative y component. Okay, so you can have vectors point in any direction. And likewise, it could be in or out of the board, and then you'd have to have another z axis. So you'd have a z component as well. But we'll just basically worry about two-dimensional vectors. All right, just a couple more quick points. We've talked about adding vectors. What about subtracting vectors? How do we take two vectors, say A minus B? If we had two vectors, A and B, how would we subtract them? Well, to subtract a vector, all we really have to do is think about adding the opposite of a vector. So if we want to subtract B, we could imagine that would be the same as adding the negative of a vector. So A minus B, we would expect to be the same as A plus negative B. But what is negative B? Well, negative B, we would expect to be a vector that if we added it to B, we got 0. So that seems right. Negative B plus B equals 0. But if we have a vector B, what would we add to that vector to get 0? Well, if we go for a walk, how would we have to walk to have 0 net displacement? In other words, to get back to where we started. Well, we would have to walk in the opposite direction, but exactly the same distance. So negative B is a vector that has exactly the same length as B, but in the opposite direction. Okay? So, very simply, when you want to subtract vectors, all you have to do is think about what is the opposite of that vector, and then add those vectors together. So a minus b is the same as a plus negative b. And we'll come back to that later on as we're doing some more work with vectors. One more quick thing. How do we multiply with vectors? Well, you can actually multiply two vectors with each other, and that's a complicated thing, and we'll talk more about that later on as it comes up. But the one thing I want to talk about first is how do we multiply a scalar with a vector? Well, let's start with something easy. Let's take 2 times a vector a. What's 2 times a? Well, we would expect that to be the same as a plus a. So a plus a, we would expect that to be the same as 2a. But what do we get if we take a plus a? Well, if we take a vector a, and then we add a to it, in other words, another vector in the same direction with the same magnitude, what do we end up with? Well, we end up with a vector that's in the same direction as a, but twice as long. So, if we take a vector and multiply by a scalar, we end up with a vector in the same direction as the original vector, but with a magnitude that has now been multiplied by whatever that scalar is. So 2a multiplies the magnitude by 2. 5a multiplies it by 5. 6 meters a multiplies the magnitude by 6 meters. So the magnitude can be multiplied by a unit also. All right, so just keep that in mind. You multiply a vector by a scalar, you end up with a vector in the same direction, unless you have a negative scalar, and then what's the direction going to be? It will be exactly in the opposite direction. So keep that in mind. You multiply a vector by a positive scalar, you end up with a new vector in the same direction. You multiply a vector by a negative scalar, you end up with a vector in the opposite direction. Okay, very, very good. We're going to be using all of these ideas about vectors more and more as the semester goes on. We're going to be using vectors a lot. So it's good to kind of introduce them now. You'll get a lot more experience with them as we go on, and there's a lot of practice for you in the homework problems. But that's all for now. See you next time.